Good morning, good afternoon, and good evening. I'm Beth Ann Noble from the Open Power Marketing team at IBM. Welcome to our second Google Hangout for the Open Power Developer Challenge. Today we're going to be talking about FPGAs and using that aspect of the technology platform in Supervessel, and also a special service that makes it easier for you to do deep learning with accelerators that's called AccDNN. So on our agenda, just a quick hello, then we'll have an introduction to Xilinx and Xilinx FPGAs. Then we'll introduce the Supervessel AccDNN service. And then we'll go a little bit deeper into AccDNN with some examples and demos. So I'd like to pass it over to just a quick moment to show you who your team on the call is. And we'll have plenty of time for Q&A at the end. So you all have met me before at our first hangout. Like I said, I'm in Open Power Marketing on the Developer Challenge team. Also, our friend Mike Hollinger is going to be available for questions and answers. He's always on Slack as well. Today we also have Fernando Valina from Xilinx, and then some members of our Supervessel team in the Beijing Research Center, Yanghua Lin, Fei Chen, and Junsong Wang. So now I would like to pass it over to Fernando Valina from Xilinx.
Hello, my name is Fernando Valina from Xilinx. I'm the engineering manager for software-defined programming tools for Xilinx FPGAs. So today I will talk about what is an FPGA, how you can use it, and about our programming environment for these devices. So the FPGA is a tiled architecture that contains a distributed set of elements such as memories, computation blocks, and lookup tables. It is very flexible in I/O interconnect, and it is low latency. These devices allow you to create custom data paths and custom hardware for your specific accelerator or application. So in terms of what is inside of the FPGA architecture, it is a column-based architecture with distributed elements that are distributed MAC units, distributed memories, and basic logic elements. And these can all be connected in different configurations to achieve a specific function or a specific application. This gives you a lot of flexibility in terms of how much parallelism your application can have, as well as what is SCXL? SCXL is our programming environment that allows you to take an OpenCL application and create a service that can run on clouds such as Supervessel and allow other users to use the power of FPGAs to accelerate an end application. So SCXL is a compile environment which will take code that was written in OpenCL, and will take kernel code that was written in either OpenCL or C and C++ or third-party precompiled libraries. This will create two executables. One will be a host side executable that will run on the IBM Power 8 architecture, and the other side will be a binary that will be executed on the FPGA. The FPGA binary will have a custom implementation of the logic needed to implement your function, and it is communicating back to the processor through the drivers and APIs provided by the Xilinx OpenCL runtime library. So without having to understand the minute details of how to communicate to the FPGA device, you can use these devices to accelerate your application. In terms of what you get out of the SCXL environment, you have a compiler which will take your code written in C, C++, OpenCL. You'll have a debugger that is based off of GDB, which allows you to do software cell debug of your hardware, as well as a profiler to figure out the bottlenecks in your design in terms of usage of memory or delays in your compute pipeline, as well as libraries. Out of the compiler, you'll get an executable for the power server, as well as the binaries for the FPGA accelerator board that is installed in these servers. We have a growing ecosystem of application developers, as well as library providers, and commodity off-the-shelf board partners. And one of our main cloud providers is IBM Supervessel, where you can use both the tools and the FPGA cards to accelerate your application. So in terms of the development flow for SCXL, the flow is separated into 3 steps. One is a functional correctness step, which we call CPU emulation, which is a functional check to make sure that your application is correct. SEXL is building hardware custom to your specific algorithm or your specific code. Therefore, it does take a little bit longer to compile than a regular compilation to a fixed architecture processor. The next thing we have to do is we have to estimate if your code will fit onto the hardware resources available on the FPGA device. Unlike a CPU architecture where code will compile and run no matter how much code it is, and what you will get is a hit on performance, on an FPGA, lines of code translate into physical resources that will be used to implement your specific function. So depending on what is your application, different boards or different devices will be most suited. And finally, we have a compilation step that will take you all the way through running your system on the board. So in terms of how to get started with SEXL and running these devices on Supervessel, we have tutorials available on Xilinx.com, as well as our documentation getting started guide. And we have a GitHub repository of pre-optimized examples that you can use as ways to learn the best coding practices for these devices. And you can take these examples and run them on the IBM Supervessel cloud as part of your Open Power Challenge development work. And with this, I'd like to pass this over to Fei Chen, who will talk about how to use FPGA accelerators in the context of neural network inferencing.
Hello, this is Fei Chen. This is Fei Chen from China Research Lab, and I'm the technical lead of the accelerator service on Supervessel Cloud. And today, me and my colleague Jin Song will introduce how to use the AccDNN service in Supervessel Cloud. Here is my colleague Jin Song.
Hi everyone, and this is Jun Song from IBM Research Lab in China, and now I'm the technical leader of the AccDNN service in Supervessel.
Okay, so I will share my screen to begin the section that we introduce our AccDNN service. Yeah, first of all, I will give you an overview of the AccDNN service. On our Supervessel, I will introducing the related component and UI with the AccDNN service. In our Supervessel Cloud, we have some FPGA and GPU hardware attached in each compute node, so that when you create virtual machine, you can attach the FPGA and GPU into your virtual machine so that you can do some programming on this hardware resource and see how speed up you can reach on the FPGA and GPU. All the FPGA and GPU management in the background of our Supervessel Cloud. So the user don't need to know much detail about the hardware management, the FPGA programming. Those details is not necessary for the user. And we provide some UI to let the user to create accelerator, to use the accelerator on Supervessel Cloud. In this left-hand side, we have an accelerator maker zone, which will allow the user to upload different kinds of accelerator. The settable accelerator can be the DNN model, which is generated from the Caffe framework, and also we support some source code, for example, the RTL code and some high-level language used by the SDXL from Xilinx. And also we support the user to upload some FPGA binary directory. Today, we will focus on the DNN support in our Supervessel Cloud. So the user have to upload the DNN network to our accelerator maker zone. In the background of the maker zone, we will do some compilation of the DNN network so that it translates into an FPGA binary, and we Supervessel Cloud manage those binary and deploy it in the whole cloud. So in the second UI, when the user create a virtual machine, he will choose an Ubuntu Linux as the operating system, and he will see some button to let him attach the FPGA into his virtual machine, and he will see a list of accelerator under his account. Those accelerator are uploaded by this user, so he will attach the accelerator into this virtual machine. And in the third UI, after his virtual machine is created, he will got his IP address of his virtual machine and got his Linux account information of this virtual machine. So he can either use the web shell to log into this virtual machine, or he can use an SSH client to connect to the virtual machine. We provide some C language API to let the user talk to the FPGA hardware. We have the API to let him open the device, transfer data from his C code to the hardware, and get back the data, get back the result from the FPGA hardware to his C code. And we have a simple C sample code to teach the user how to do with the FPGA hardware. So I will turn to my colleague Jun Song. He will give the user more detail about how to use the AccDNN service.
Okay. So I'll give all of you something about the technical detail of the AccDNN. Here is why we want to propose such kind of service in Supervessel called AccDNN, because there's a lot of people, especially for the data scientists, they cannot do the RTL code for the FPGA because it is very special. So and it will take a long time to do the simulation, to do the compile, and do the test. So here we want to propose a service that can convert the deep learning model to FPGA directly without any programming. So here is the whole architecture of the workflow. People, if you're familiar with the cafe framework, so they can use the GPU in the Supervessel to train their own network model using the GPU and their own data. After that, they will generate a model. That should be contain a net file and a model file. And our AccDNN code accept such kind of DNN network and model file into FPGA bit file. And in the Supervessel, just like Chen-Fei said, so we can provide a service to download such kind of FPGA to such kind of bit file to FPGA, and provide the FPGA accessible in the virtual machine. So you can write your own code on the Supervessel virtual machine to do some application and use this FPGA. Next, here's the framework of AccDNN. So when people input their the protocol buffer like the network definition in the left button. So you can use some convolution layer, polling layer in the production layer, softmax like that. It's a traditional convolution network. And we can translate this network to a Verilog source file. And after that, we could use the Xilinx compile tool to compile the source code, the RTL source code to FPGA bit file. And then we download to this bit file to FPGA execution. So here, the main difficulty and also the critical component is how to translate the net model to the RTL Verilog file. That is the key point. Okay, And this chart we also show something about the workflow of the AccDNN. Currently, because we will build up a basic IP like some controller, like some vector multiple adder, like some vector max, and I use such kind of very small hand coding like lib, and we could use this kind of lib to build a spatial layer, such as convolution layer. It should be used some vector multi-adder, and we can also use the lib to construct max polling. It should be used the vector max, and use this basic lib. We can build many kinds of convolution layer with different configurations. And we use a standard I/O to put this several layer together, and also add the CAPI interface to this network, so that it can be final generator end-to-end source code, and then we will use Xilinx tool to compile the whole network. So you will see that here only the basic lib are hand coding, because this is a very basic lib, and other things, especially for the to constructors basic lib to the specific network, and the whole layer also with the interface are all generated by automatically. Okay, so here in section 3, I would like to introduce something about how to use our GPU acceleration to generate a cafe-based DNN network. So here, because the DNN, the cafe distribution provided in this challenge is something specific for IBM. So it's a little different from the community versions. In this version, there's no very special demo or very special examples. So I just write a sample demo in this GitHub. Everybody should have access to this because it's public. So okay. So let me to show these demos. Okay, so let me to this Supervessel dashboard, and in the image marked, we click the image marked. And we show the open load challenges. So we could see we could use this open load quick start to create your virtual machine here, because at the same time I have created a virtual machine for in the dashboard, so we can come back. So this is the virtual machine I created. So we can use the web console to log in. Okay, so we use the OP user password. Okay, so it's much better to use root command. So we go to okay, so we can make a test. we can to get clone this demo the demo source code. Okay, so very quick. Here we have several tools. So here we should to first to go into the data directory, and you can use this script to get the data. Because the network is a little, so we can wait several time to wait the download is completed. And because this if people use the competitive version of the UC Berkeley, so it's this demo should be inside the distribution, so people also don't need this source code. Okay, so we use the upper layer, and we can use this script, the create cipher turn sh, and this script could convert the source data, the raw data, to the LMDB file, and this data could be trained using the config model. Okay. Okay, so because this version is the IBM version, so we should still remember to use this command to source the IBM version. So this command is very important because there's a lot of framework in this image. So you need to first use this command to enable the config first. So we can use. Okay, so we get so here we have generated two lib, and one is for the training, and another is for the test of verification. So here we can use the train the quick. We can start to train a very small models. So let me train. So we can up to the. It will take some time. So after that, it will generate models, the network model and a model file, and we can we can package these two files into a zip file, and so it will, because the training will take several relatively a long time. So to save time, we can go to the next step. Okay, let me to see the section 4, and after training the model, we can we can use this model to in the Supervessel cloud use the AccDNN service to convert this trained DNN network to a real accelerator based on FPGA. So it's finished. So it's we just because we need to log in first. And we click the new DM buttons, so we can use this test save as a name. There's a save demo with some descriptions. And select here we use AccDNN. So here we should to select the file we just on the previous training process. So after that we click the submit. So it will appear here. So because the compilation time is we should take a long time. Maybe take several hours based on the size of your network model. So after this all box becomes green, the AccDNN service has completed converted the DM model to the FPGA accelerator. Okay, so next session, I would like to give a demo about how to use this FPGA image. And we come back to this here. So we go to the instance. So we could launch an instance here. And select the doc image. And we use the FPGA accelerator. So here we have the ACC. So and this name should be in the previous step you have upload ACC DM model. So the name you used inside the web page should be appeared in here. Because it will take a long time, so I just have prepared my own image here. So we could use this to create AccDNN based image and create a launch. Okay. Now here's building. So it will take some time. So we can first go through the code here. Okay, it's okay now. So we can to use this console. Here, because it is a new image, so we first to change the password. So it's much better to use root account. We also need to change the password. Okay, so we so here it's much better to we can use this so we can use this GitHub. It should be in the README of the this challenge. And you could use this link to copy to fork a code here. So we could use here to use this LeadMe, so we should to first to install some lib for this AccDNN driver. And then here we have application to about how to use. We just uploaded the CFA demo to how to it tell us to how to run this demo. So he used give us the final result, because CFA is the 10 classes, so it give us the 10 values, because currently we don't have implement the softmax layer, and so it just give us the value just before the softmax, and then we could just select the biggest value, such as the index of the biggest value, to as output of the final classification result. So and here we in such kind of a very short time, it has run 10 loops, because each loop is very small, so we can see some acceleration in this demo. So here I will also have a little time to just give a description of about the code here. Here is the example code. So I just take a little time. Okay, let me zoom out. So first of all, we needed to allocate a memory for the application to transfer the data from the host to the FPGA, because it is KP based. So the FPGA could directly access the virtual address of the host memory. So it's needed to do the memory copy from the kernel side to the application side, and that will significantly reduce the latency of the whole loop. And here we first to open the image file, the image, and get the data here. And here we just to open the KP device. It will automatically find this KP that attached to your virtual machine, and open it. So here we just write 100 loops. So because it's the FPGA could work in a pipeline mode, so it is much better for user to write a multi-thread model to use this code to use this FPGA accelerator. So here I just give a simple example here. So but I didn't use the multi-thread here. So it divides the whole process into two parts. The first part is the transmission, transfer the data from the host to the FPGA, and the other process is to get the results from the FPGA to the host side. So it has status bits. So we just to check status bits, and if it is set, so some translation is finished, and we can get the data and then we clear this bit, and we to wait for the next translations. So here we just give some simple example. So if people want to write some very complicated code, it is much better to write a multi-thread framework to better exploit the capacity of the AccDNN to exploit the pipeline feature of the FPGA. Okay, that is all the AccDNN service in Supervessel and all the demos here. So let me share this screen to
Thanks, guys. So this is Mike Hollinger, and I've worked with the guys in China Research and with the CAPI team. Ishan is actually here with me from our CAPI development team. I wanted to pop up and actually point out that we have a question in the Hangout Q&A. So briefly, Kiran Mehta asks, I am new to both neural networks as well as FPGAs. Can you very briefly explain terms like convolution layer, what really makes up a neural network, what is a neuron, and kind of give us that really brief overview here.
Okay. So okay. So that means in the convolutional layer, so people would like to such kind of the kernel size, the stride, such kind of parameters to configure the convolutional layer, because it is also the key point of the country popular deep learning network. So currently, the AccDNN could support up to to be honest, this is based on the size of the FPGA. If you have a relatively large FPGA, it could to support a very deep convolutional layer. And if your FPGA is relatively small, so maybe somehow a large network cannot be supported. So it is based on the size of your network. So in the country in Supervessel, the FPGA size is somehow is a middle size in the Xilinx series. So currently we can support up to 14 layer of the neural networks. And somehow because the size, the FPGA size is somehow is not very large, so we cannot support such kind of large network such as the Google network, the VGG, such as some the AlexNet like that. But we can do some small or to medium network. And in the future, we are also trying to develop the version, the AccDNN version 2, to use the external DDR and use several FPGA to work together to make the AccDNN could support a very deep network. Okay.
Cool, thank you. By the way, I would also encourage everyone to please ask questions in the Hangout here or even in the Slack that we have configured. So if there are further questions, we can continue to work through those.
Okay, well, yeah, Kieran, I see your second question, and I apologize. I'm not sure that there's much that we can do about that, but this will be on YouTube for a replay, and it might work better for you there. But you can also find us on Slack pretty much all the time. We have the global team, and at least some of us are always online there to answer your questions. But thank you for those, and sorry we couldn't help you with that. So I guess I don't see any other questions, but I want to thank our team from China Research, Mike and Ishan, and Fernando from Xilinx. We will have more Hangouts coming. We have one next week, really focused on GPUs, and we'll have another one more about with the Xilinx team, focused on FPGAs. So find us on Slack. Actually, sorry, there was just one more question that came in from Corey Han. Do you need the Xilinx tools? Corey, could you submit?
Yeah. In the converter process of the AccDNN, it don't need the Xilinx tool. It's just we just build our service ourselves. We just you can use. The only thing is you need to install the config. That is the only dependence.
Yeah, here is more comments on this question. In our cloud environment, of course, we have the Xilinx 2 running in the background, but for the end user, he don't need to explicitly use the Xilinx 2 in the web UI. So we will handle all the compilation in the supervised cloud background.
Yes, but okay.
Thanks, guys. And Corey, I saw your other question about the specs on the different FPGAs. We can make those available to you. I don't think we could share it right now. It's probably easier to follow up offline with you. So if you're participating in Slack, just ping with the same question there, or you could answer, I guess, ask your question in the form of the DevPost challenge. In any case, we'll find a way to follow up with you and get you that information.
Yeah, Corey, in Slack, if you poke me, my handle is MikeH-IBM. We can chat there. What I'll do is I'll go grab some stuff and try to put together a little dossier of, here's the hardware and the specs that are kind of running underneath the covers. Because it's really kind of interesting, right? So I'd be happy to share that. And I think other people would benefit from it too. So we'll handle that over there.
I see the question from the Corey that asking whether there is a different FPGA in our supervised cloud. The answer is yes. We support hybrid type of FPGA in our supervised cloud, but we don't expose those details to the user because we don't want to confuse the user. All the difference image, FPGA image in our supervised cloud is handled in the background. But of course, if the user want to know more detail about the FPGA, we would post those FPGA types series number in our wiki page. And please take attention to our wiki page. Thank you.
Yeah, Corey, and I saw you on Slack, so we'll be over there in just a sec and make sure we can get you what you need there. Thanks for your question. Okay, well, I don't see any more questions coming in. I think with that we can end our broadcast. And thanks everyone for taking the time to join, and thanks again for the team for presenting. And we'll see you in Slack and at the next Hangout that we have. Bye, everyone.